Thermodynamics. Here we've got a problem. Well, let's just draw it out on the PV diagram. We're starting at a certain condition. I'll just put a dot here. Call that point A, I guess. And we're going to add some energy. We're going to heat up our gas. In this case, it's helium, which we're going to treat as an ideal gas. And we're going to heat it up at constant volume. So the pressure is going to increase as we move from A to B. And then we're going to let that gas go through an isothermal expansion back to the original pressure. Call that point C. And then an isobaric compression back to point A. So we make a complete cycle going from A to B to C. I've labeled those endpoints, those conditions that we're moving from one to the next, A, B, and C. And the first thing I like to do is figure out what's happening at each one of those endpoints. So let me make a little table to kind of guide me here. So point A, B, and C. And what do I want to know? I want to know the pressure. I want to know the volume. And I want to know the temperature at each one of those points. So let's work on filling out this table. That's the first thing I do. When I get a problem like this, I make a table with all the endpoints, those conditions that we're moving between, and I try to fill out the pressure, the volume, and the temperature for each of those points. And the next thing I do is I make a table for the paths between point A and point B and C, and point C and A. And there we're looking for work done, heat added or removed from the system, and change in internal energy, but you'll see that next. Okay, so here are our points, and the first thing I'm going to start off with is just sort of figuring out what I know and start filling some things in. So I know right off the bat that T, the temperature at B, is equal to the temperature at C, because that's an isotherm. And I think that was given. That's our maximum temperature. And that was given 327 degrees Celsius, which is 600 Kelvin. So I'll go ahead and pencil those in. Let's see, we've got the temperature at B is 600 Kelvin. The temperature at C is 600 Kelvin. And the pressure at A is equal to the pressure at C, and I believe that was given. So we'll put those numbers in. And the pressure at B was also given, right? 3 times 10 to the 5th pascals. Okay, so now we have to figure out everything else. And because we can treat this as an ideal gas, we can use the ideal gas law, PV equals nRT. So the first thing I'm going to look for is the volume at A, which is also equal to the volume at B, because it doesn't change there. And that's going to be nRTB over PB. And what is that? That's 2 moles times 8.314 joules per mole Kelvin times 600 Kelvin all over 3 times 10 to the 5th pascals. And that leaves me with my answer in cubic meters. The volume is 0.0333 cubic meters. And I can do the same thing for point C. And I've got 2 moles, 8.314 joules per mole degree Kelvin, 600 Kelvin, all over 1 times 10 to the 5th pascals. And that gives me a volume of 0.0998 cubic meters. And then the last thing I can solve for here, I believe, is the temperature at condition A. Pressure times the volume over nR. And what do I get for that? 200 Kelvin. So let me go back and put those numbers into our table. 200 Kelvin for that temperature at A. The volume at C, 0.0998. The volume at A and B, 0.0333, and those are cubic meters. Pascals for pressure, Kelvin for temperature. Okay, so that's the first thing I like to do, figure out what's happening at those points that we're moving between, point A, point B, point C. Pressure, volume, temperature. Hopefully we have an ideal gas, because that enables us to use the ideal gas law and figure out the missing information.